Welcome everyone. In the last 4 weeks for this Silicon Valley Chapter Challenge, we were all working together with the collaborators around the world to find a safe path to travel in the aftermath of an earthquake. So this is with the Omdena Silicon Valley, and Nishrin is the chapter lead. We'll start with the problem statement. So the problem statement given for this challenge was California is usually prone to earthquakes. So we wanted to find how to prepare the city, how to respond to the earthquake. And the goal was to find a safe and a fast route to evacuate after an earthquake. So there were some high-level tasks given to us as part of this challenge. There were 4 different high-level tasks is to kind of segment the buildings and the street, and then based on the segmentations, do some kind of a distance risk scoring, and then use the pathfinding algorithms to find a path from a source A to a destination B. And we wanted to integrate it with the heat map. The heat map, the metric for the heat map would be the risk score. This was our approach. And a small prototype was made. So we considered 5 different risk factors. The 5 different risk factors are density, width, speed, distance, and liquefaction. And we did it for 3 neighborhoods in the San Fernando Valley. The 3 neighborhoods are Northridge, Chatsworth, and North Hills. And we also included some possible safe destinations that people might want to travel during or after an earthquake. And those safe destinations being shelters and parks. And we have 5-task team across collaborators, and this information was assembled. We did some risk factor analysis, combined the risk score, and then that was fed into the downstream pathfinding algorithm. So we will take you through all the different risk scores that was considered as the part of this project. So like we said, we have 5 different risk factors. So the first risk factor is the building density. The intuition behind this risk factor is that large number of buildings on a given road or a neighborhood would pose a larger danger during an earthquake. So the approach, the way this risk score was calculated was we divided the neighborhood into grids, into a 20 by 20 grids. We extracted a total number of buildings from the OSMNix API for that grid, and then we applied those total the building value on all the edges in that grid. So the good thing about OSMNix package is it allows the nodes and the edges are stored as a geodata frame. So it allows you to manipulate the underlying graph and to also include new values or attributes on the graph that you could use later. The second risk score was liquefaction. So liquefaction zones are defined on the website by GeoLA website, and where liquefaction zones are identified where the stability of the soils needs to be investigated. So we downloaded the data from the website, and the downloaded data was in the form of the shape files. So we downloaded for the relevant neighborhoods, and then the edges in the graph were compared with the geometry of the shape files. If the edge is inside a particular polygon, then it's associated this factor, liquefaction factor of that polygon is put on that edge. Third risk factor, the third risk score that we used was the road width. Here, the intuition was that the roads with a wider width are more safer than the roads with narrower width. And the approach that was taken is, again, there are road categories and different road types and the edge property called highway in the OSMNix package. So we converted those categories into discrete numerical values, as you can see from the table on the right-hand side. And once those categories were converted into discrete numerical values, those values were stored again on the edges. And you can also see the heat map at the bottom of the page with different edges, numerical values in the heat map. And the next risk factor was distance. The intuition here is the farther a road pixel is from the building, the safer it is. Normally you would need machine learning models to segment the buildings and the roads. But with the OSM Next package, we have a building's footprints, which is available using API function. So we use the building footprints from there, and then those building footprints are used to calculate the distance transformation. And once the distance is calculated, the risk associated with that edge, that is the average distance of that edge from the nearby building, is included on the edge of the graph. In the next slide, we'll look into this into more detail. So the left-hand side is the building footprint, which is plotted using the OSM Next function. And if you zoom into that, in the left-hand bottom corner, you will see the footprints like so. And once the distance transform function is applied, the image is transformed to the one that is in the right. And the white against the black background is actually the integer value of that pixel from the background image, that is the buildings in this case. And if you take those integer values, you sort of see in Excel over here, again, the red represents the buildings because it's having a 0, which corresponds to the RGB color of black. And the yellow around the building is the integer value, that is the Euclidean distance of that pixel from that building. And the green around that it means it's farther from the building, and hence it has got a higher integer value. And that you could zoom out and you could see the integer value on the right-hand side. And the last score that we used was the max road speed. Max road speed is a proxy for wider roads and hence more safer. So we did some kind of imputation here where there were some max speed values were missing in our submit. And then the roads with higher speed were tagged with a smaller risk score, but those with low speed were tagged with a very high risk score. And again, the speeds were converted into a discrete integer value. You can see from the right-hand table where 4x stands for any road with speed of 45 or 42 getting converted into a risk score of 6. And once these risk scores were calculated, we combined the risk scores and the neighborhoods. Since it was done by a lot of collaborators, all the risk factors calculation was done in parallel. So in the end, once the data was assembled, it was combined as a part of this integration step. So first we combined the risk factors, and then we combined all the 3 neighborhoods. And then the last thing in the integration step is to add in tag special nodes as evacuation nodes. And the evacuation node is of the type shelter or park. And once that data is assembled, it is now available in a combined graph with the node stack with all the risk factors on the edges and available for all 3 neighborhoods. And that's how the combined risk score. So after the data is integrated, then risk analysis and a combined risk score is calculated. So on the left-hand side, you could see the 5 different risk scores. So we have distance, liquefaction, speed, width, and density. And they are all heat map color coded using the seismic C map, which is same across the different plots over here. And once there was a correlation plotted, we could see that like the max speed and the width has got a very high correlation. And so we decided that we should give them a 0.5 weightage instead of having an individual weightage of 1, because they would dampen the effect of other risk factors. And also from the liquefaction graph, you see we only have values of 0 and 1. So which is a problem when you combine risk score. It will, if we don't dampen the factor of liquefaction, you'll immediately see that the area on the right would be considered very safe, no matter what other risk scores are integrated in it. So that factor was also dampened. And once it's combined, it normalized to having a risk score between 0 and 3.15. And it's plotted in the graph below. So the below graph is a combined risk score. And the blue lines over here are considered very safe versus the dark red are the most riskiest. Any color in between case the varying degrees of risk on it. From here, I will be handing over to Joyce, who will take us through the pathfinding part of the process.
Thank you, Sanjana. Yeah. Can you see the screen?
Yeah.
Joyce.
Thank you. So the next task is the pathfinding.
Joyce, we can't see.
You can't see?
It seems blank. Where you wanted to
I think we can. You could see the screen, but it was just a browser, I think, that had opened up. At least that's what I could see.
Oh, you can't see the presentation.
No.
No? Can you see it?
Yes.
Yes.
Thank you. So the next task is the pathfinding. In the pathfinding, we use 3 different algorithms. We used Dijkstra, we used A-star search, and hierarchical A-star search. And we analyzed the performance of all the 3 methods using the average time taken, the total length of the path, as well as the total risk associated with the paths. Okay. So now we will have a quick summary of all the 3 algorithms that we used. Let's suppose a human being is traveling from a source to a destination. If you look at the GIF here, you could see that the green cell over here is the source and the red one is the destination. So we could see that the destination is at the top row. So if a human being is traveling to that point, he will try to reduce the distance to that point. So he will always try to move up. So A star is using such kind of a logic to reach the destination. In order to do that, it uses a heuristic f of n equals g of n plus h of n, where g of n is the cost of a node from the source and h of n is the estimated cost from that node to the destination. But if you look at the Dijkstra algorithm, it doesn't consider the location of the destination. How it explores a node is that it chooses the node which is closest to the source. So even if the destination is at the top row, if the algorithm knows that a node is close to the source and it is moving downward, it would only explore that node, then only it will come up. So the problem with Dijkstra is that it expands the search in all the directions. Even if the destination is at the top, it will move downward on all the sides. So the problem is that it explores a lot of nodes, but in A star, it will reduce the number of nodes being explored. But the problem is that if the path is less, there is a computational time needed to compute the heuristic. So as the length of the path increases, A star search would outperform Dijkstra. Now we will talk about the hierarchical A star search. What we do in a hierarchical A star search is that we will do some pre-computations to reduce the runtime. For that, we will take the graph of the region and then we will divide it into several clusters. And for each cluster, we will define an entry point as well as an exit point, and we will find a shortest path from this entry point to exit point, and this one is pre-computed and stored. So whenever a search is performed, we use these values so we can reduce the runtime. For example, let's consider a small graph. Suppose we have 4 clusters, A, B, C, and D. And let's say they are arranged in a row. So A has the neighbor B, after B we have the cluster C, and after C we have the cluster D. So let's say we have a source in the cluster A and a destination in the cluster B. So what this algorithm does is that it has already predefined the entry point and exit point for each clusters. So if you want to cross a cluster, then it will take the shortest path or the safest path from the entry point of that cluster to the exit point of that cluster, and it will be added to the path. So when we are traveling from A to D, it will take the source in the cluster A and it will compute the best path to the entry point of B. And in order to cross the cluster B, it already has the path. So it will add that path and it will reach cluster C. For cluster C also, it's already computed. So it will use that. And then the algorithm will compute the value from of going from the exit point of C to our destination. So the problem is divided into X sub-problems, where we already have pre-computed the solution for X minus 2 sub-problems. So we are computing only the solution for 2 sub-problems. As a result, we are reducing the runtime of A-star search in this approach. Now we'll move towards the implementation of our algorithms. Suppose a person want to travel from source A to destination B. So if we give the shortest path, he can reach there. So we have marked the shortest path in this red line, but after an earthquake, we are not considering the shortest path. We should give the safest path. So in this plot, the yellow one is the safest path. This one is the safest path, but there's a problem with this approach. If we give the safest path, the thing is that let's assume that I can travel from A to B in 20 or 30 minutes if I use the shortest path. The safest path only considers the risk score. So let's say the user searches for the safest path and it will take a long time, like maybe 5 hours to reach that path, that point. So the user won't be satisfied with such kind of a result. So what we want to do is that we have to combine the risk score as well as the length. So we have to find a good combination of the combined score and length to get a path which is safe as well as which is short in terms of length. So we use different approaches. We try to normalize these values. We try to add the risk score and length, and we try to take the product of this. And this is a plot which shows some of these approaches. And we tried it for several pairs of source and destinations. And what we realized is that the product of the combined risk and length would give a good path where the length is reduced and as well as the risk is also reduced. So this green line is that kind of a path where we have used the combined score into length as the metric for that. And this is a heat map which compares all the 3 paths, which is the shortest path. This red one is the shortest path. This blue one is the safest path, and this magenta colored one is the best or optimal path where we are reducing the distance as well as the risk score. If we look at if we have a closer look here, we could see that the risk as well as the length associated with the with the best path or the optimal path is in between that of the shortest path and the safest path. And the next one is a comparison of all the algorithms that we have used. So we have compared the algorithms in terms of the total time, total risk, as well as the total length. So if you look at the total time, we could see that hierarchical A-star search is always giving the best results. So our main motive in doing the hierarchical A-star search was to reduce the runtime, and we have achieved it. If we look at the other 2 factors, we could see that it's A-star search and Dijkstra which is performing well. They are giving the least risk as well as the least length, but a hierarchical A-star search is not able to give the optimal results, but we could say that it is giving a near optimal result. The problem is that in hierarchical A-star search, we are pre-computing the values to cross a cluster. We already define an entry point and exit point, and we find the best path to reach exit point from entry point. But depending upon the values of the source and destination, this may change. Like we may not have to pass through this entry point and exit point all the time. There would be a better path which doesn't go through these points, and that's why we are not able to get an optimal path. But still we might be able to make it better. And now we have a dashboard for our project. So this, so we have a Streamlit application, a web application. In that we have used a star search with heuristics, and we have taken combined risk into length as the weight. And in this one, we can give our current location, and we can search for the nearest shelter, nearest park, or we could also search for a custom destination. And this is also a heat map with all the parks as well as shelters in the region. So we can see which area is safe, and we can move to a park in that area also. We have also developed a mobile app, and in this one we can give the current location, and we can search for the nearest shelter as well as the park, and the technology used is PyQt5. And let's move to the future work. In this project, we have done this only for a small region of Los Angeles. We have used only 3 neighborhoods, but we could scale it to the entire city of Los Angeles, or we could even do for the entire state of California. And domain knowledge is an important factor when we do a project in data science. So a better understanding of the risk scores and their relevance to earthquakes will help us to make a better result out of this project. For example, there are factors like height of the buildings, age of the buildings, etc., that we didn't include as a risk factor. So we could use these and make a better risk score. We could also experiment with different weightages of the parameters and experiment with a star search to find a better weight and a better heuristic that would also improve our application. And once the application is deployed, we can use past user experience to improve the application. Also, we didn't use any real-time path adjustment. This could be done to improve our project. And our source code is available on GitHub. The link is given here. And the tools and programming languages used include Streamlit, which is used for making the web app. And we use Google Colab and Python. And we use QGIS for making some maps. And we use PyQt5 for the mobile web app. And the libraries include OSMNX and NetworkX. OSMNX was used to get the data related to the region. We got all the road networks and buildings using OSMNX, and NetworkX was used to implement the pathfinding algorithms. We have also used some external data sets. We used one for the shelters and another one for the soil liquefaction. And we would like to thank our team lead, Nisrin Kashwala. Nisrin is the chapter lead of Omdena Silicon Valley Chapter. She's an awesome leader, and she was always supportive throughout the project. And we would also like to thank all the task leads, Sanjana, Soham, Joyce, Rhey, and Hussein Rawat. And we would also like to thank all other collaborators. Special thanks to Adarsh, Jaya, and Isha, who worked on this project. And thank you all of you for listening to us for this time. And now we will have a demo of the app by Rhey.
Thanks, Sanjana. And Joyce.
Can you see now my screen?
Yes, Rhey. Yes.
Okay, so in this part of the presentation, we'll take a look on the sample web app that we have created to visualize how the user could use the modeling that we have created. So for example, we can input here the location that we have, and then we could have a multiple selection. For example, we use the nearest park and shelter as one of the safest place to go, and then we also got the custom destination. So let's try first the nearest park and shelter, and then we could see here, so the green one represents your current location, and then those two items, this one represents the nearest park, and then this one represents the nearest shelter according to their safetyness. So we also put here the path length and then the total risk for each of these items. And then you could also see, for example, if you just wanted to go to the nearest park, so you could select the nearest park destination, and then you will just see one path going to it, which is the park. Lastly, so we also got here the custom destination. Um, so for example, if you wanted to go to this location, so you can just input it here, and then the same thing will happen. This will show you the path going to that particular place, showing what's the path length and then the total risk. And then the green one still corresponds to the current location, and then the red one corresponds to the destination. So lastly, we also added here the maps that the heat maps of the whole neighborhood. So we can see here also the evacuation markers wherein we set it as the green ones is the park, and then the blue one will be the shelters. So we can see here the heat map. So what does the color represent? So the blue one represents the safest path, while the yellow one corresponds to the safe path, and lastly, the red one represents the dangerous path to go during an earthquake. So that's all that we have. Thank you so much for listening.